Hello everybody. So, in the last class we were talking about what sort of interactions are generated when the high energy, high velocity electron beam actually bombards the specimen, right. We looked at different types of possibilities from different depths within the material. Okay. So, now let us take a look at some of the primary aspects as we discussed earlier. We will primarily look at backscattered electrons, secondary electrons and characteristic X-rays that are coming out of the specimen, because that helps us especially with respect to cementitious materials. The most widespread applications of scanning electron microscopy are in these three domains. So, let us first talk about what are these secondary electrons. Now, you know very well the structure of an atom, how the electrons are held in these shells that define the approximate electronic positions around the nucleus, right. So, you have an incident electron, right, which is from your electron beam, which may come in and knock off a loosely held outer shell electron. Okay. So, this electron is coming in and knocking off an outer shell electron. Now, these electrons which are getting knocked off from the outer shells are going at very low energies, typically about 5 to 10 electron volts. Okay. So, up to about 50 electron volts, the low energy electrons that are dislodged from the electronic shells by the incident electron beam, these are called secondary electrons, right. So, these electrons are getting dislodged from the outer shell and now these need to be collected. Since they are low energy, all you need to do is give a sort of a arrangement where you have a positive potential like 100 to 300 volt potential, and these electrons are simply attracted towards that potential because it is a positive plate, and these electrons simply come directly to that plate, or it is also called a Faraday cage detector. A secondary electron detector is nothing but a Faraday cage. It is a positively charged plate which attracts the electrons which are generated from the specimen because of these secondary interactions. That means, incident electrons knocking off loosely held outer shell electrons. So,
exactly try to displace the atom from inner shell.
Yes, yes. So, I will come back to that. Those are the kinds. So, the question is, in X-ray diffraction, the incident beam basically knocks off the incident electrons which are generated in the X-ray tube, knock off the inner shell electrons of the target metal, because of which you generate characteristic X-rays. But here this beam is only knocking off the external electrons. There will be internal electrons also, we will come to that in just a minute, but external electrons getting ejected are loosely defining the morphology of the object. So, if you collect the secondary electrons that emanate from the specimen, you can now make out the external structure of the material, because we are collecting these from a very shallow depth. I talked about this earlier, that we are actually collecting secondary electrons only from about 100 angstroms, that is about 10 nanometers, okay, extremely small depth within the specimen. So, we are essentially looking at the structural features of the surface when we collect the secondary electrons. So, these secondary electrons are collected by the Faraday cage, and basically there is some sort of a multiplex, or rather photomultiplier, which ensures that the signal that you get can be amplified significantly to generate the right kind of image. Okay. Now, of course, we will talk about how morphological information can be obtained based upon the characteristic shape of the crystalline materials that you are actually trying to observe. So, if you look at a typical sample for secondary electron microscopy, we talked earlier that sample preparation is not really anything for secondary electron microscopy. You just need to fracture your sample and stick it under the microscope, right. Of course, for ceramic specimens and for cementitious specimens, you need to coat these samples, right. So, because of that, of course, because of the fracture, you have these relief features on the surface. You do not have a flat surface, you are not cutting the specimen, okay, you are simply fracturing it and putting it. So, there are these relief features, like you have these crests, you have crests and troughs on the surface. Now, what will happen is the incoming electron beam, if it is striking the location of the crest, what is going to happen here? Because the secondary electrons that are generated here are generated from the very top of the sample, okay, there is a good chance of collecting everything with the detector, since the electrons are getting ejected from the top or crest of the sample, it is very easy to collect a lot of these electrons. So, in other words, how will this crest appear in the microscopic image? It will appear bright. Okay. On the other hand, when you have a trough, a lot of these secondary electrons that are getting out may not get a chance to completely go towards the detector, because they need to go across all the valleys and hills that are available on the surface to really make it to the detector, secondary electron detector. So, many of these electrons may not be able to get detected by the secondary electron detector, because of which the troughs will appear darker in color. So, here you are able to now resolve minor changes in the heights or levels of different aspects on the surface of the specimen. Now, of course, this is not just minor. If you once we look at the kind of depth of field that you can get, you can actually look at even millimeter sized defects as far as scanning electron microscopy is concerned. You will be able to resolve as much as low as a few nanometers and as high as a few millimeters. That means not only do you have a good resolution, you also have a good depth of field. Okay. At the same time, keeping more than 1 millimeter of the specimen in focus is something of a wonder as far as microscopy is concerned. You can never do that in optical microscopy. In optical microscopy, you have to work with flat images, right, when you are looking at reflectivity, and you can't simply get any way that you can extend the depth of field beyond a few microns. You will not be able to do that. Okay. So, because of this possibility of collecting these electrons even from deeper and higher regions within the surface of the specimen, you can then distinguish features that are separated by a significant amount. So, that is the reason why your scanning electron microscope or secondary mode imaging can have a very high depth of field. What about backscattered electrons? Now, we are talking about scattering of the incoming electrons by the atomic regions of the sample. That means the atoms of the sample are scattering the incoming radiation. Now, scattering can happen in all directions, right? Scattering can happen in all directions, but you know that the heaviest part of the atom is the nucleus, and when this incident electron comes and gets scattered by the nucleus, there is a good chance that you get a completely elastic scattering, because electron mass compared to nucleus mass is hardly anything, negligible. So, if it hits the nucleus, it is going to get scattered quite significantly back in the same direction. So, basically these are elastic collisions that arise between the incoming electron and the nucleus of the target atom. Now, for collecting more number of, that is why the backscatter detector is placed right around the objective lens. So, that is the objective lens here, and that is the backscattered electron detector, right. I told you earlier that it is an annular ring just around the objective lens, so that all the electrons that go and strike the specimen can come up straight up almost with a 180 degrees turn in their path and get detected directly by the detector, which is placed right around the objective lens. So, there is, because it is elastic scattering, there is very little change in the energy of the scattered electrons, but there are of course other inelastic scatterings that are also happening. I told you from this picture here that there are a lot of other things taking place. You can have inelastic scattering, you can have transmission of the electrons through the specimen and so on, depending upon the energy of the electrons and the density of the phases that you are trying to observe. But we are interested in backscatter electron primarily from the point of view of the elastic collisions that are happening. So, generally because the scattering can happen in several directions, only about 1 to 10% of the electrons which are getting scattered can be collected by the backscatter electron detector, because only some of them will have a completely 180 degrees reversal in their path. Many of them may just stray off to the sides. We do not collect those electrons, we primarily collect the ones which are coming directly back. Okay. And the denser the phase, right, the greater will be the reflectivity, because if the nucleus is dense, you can imagine the elastic collisions will be much more from that type of a nucleus. Also, please remember there is the other issue, the denser the phase, the greater will be the absorption also, right, and the denser the phase, the lesser will be the penetration depth of your electron beam. So, to ensure that you get good penetration, what should you do for the electron beam? Increase the accelerating voltage. You need to increase the accelerating voltage to get good penetration. If you are looking at very dense phases, you need to work with high accelerating voltages. Nevertheless, these electrons that are going into the sample are then getting scattered by the nuclei. Some of the scatter happens directly back, that is the elastic scattering, which results in very low change in energy, and these electrons can be detected by the annular ring placed around the objective lens. Okay, that is the backscattered electron detector. Now, of course, the type of detector and the composition of the materials that make up a detector is of course probably beyond the scope of this course, but then again what we want to understand is what is the kind of material it is made up of. It is basically made up of the same kind of materials that we call as semiconductors, right, solid state devices. So, if you remember some part of your physics about semiconductors, there is a valence band, right, in which, so the electrons, when you supply energy to the semiconductor, there is an electron which is basically transmitted from the valence band to the conduction band. Okay. So, again when a backscatter electron strikes the detector, electrons in the material move from the valence band of the semiconductor. What type of materials are semiconductors? What is the most common element that is used? Silicon, right. Silicon, germanium, these are elements that are used to make semiconductor devices. So, here you have what is known as a valence band and a conduction band, right. So, when you have a backscatter electron which is striking the detector, it is moving the material in the electrons in the material from the valence band to the conduction band. Now, the electrons in the conduction band can either continue to move in the same band or drop back into the valence band. Of course, for stable configuration they need to drop back into the valence band, but what happens is if a potential is applied, you can now separate the electrons and collect them and measure the actual current in the detector, okay, because now these electrons in the conduction band you can actually then start separating them and measure the current in the detector, and the strength of the current is proportional to the number of backscatter electrons that hit the detector. So, more number of backscatter electrons hitting the detector will cause more number of events of electrons in the valence band moving to conduction band. So, there will be higher current, right, and that current can then measure the intensity of the backscatter electron collection. So, what you need to remember first is electron beam striking the sample, more backscatter will happen for denser specimens because there will be greater mass of the nuclei. So, there will be elastic scattering, and these electrons are collected by the detector. Within the detector, the electrons go and strike the solid state semiconductor devices like silicon or germanium, typically silicon devices, and transfer the electrons in the valence band of silicon to the conduction band. And when the electrons are moving in the conduction band, you can measure the current in the conduction band, and that current is proportional to the number of times this detector has been hit by the backscatter electrons. Okay, so that is the simple schematic principle of how a backscatter detector works. Of course, you have to be a material scientist to fully appreciate how solid state devices actually work. So, it is beyond the scope of our understanding here, but again as I said, your backscatter detectors are typically placed around the objective lens, and generally if I draw the annular ring like this, it is usually divided into 4 quadrants. This annular ring is typically divided into 4 quadrants, and each one of these is your solid state device. So, again there is some averaging that takes place to determine what exactly is the intensity of the backscatter electrons that you are collecting in this solid state device. So, again this is just showing you the atomic weight effects on the number of backscatter electrons that come out. So, with the atomic weight, the amount of secondary electrons that come sort of saturate out, but the amount of backscatter electrons can have a significant increase with the increase in atomic weight of the sample. Now, of course, beyond a certain point this also starts getting leveled. Why do you think this happens? Why does the intensity of the backscatter electrons that you can collect sort of levels off after a certain atomic weight is reached? Why is that happening? More scatter and more absorption, right? There is a lot more absorption. So, beyond a certain atomic weight, the effects of the absorption will be dominant. Absorption effect will be dominant, because of which the backscatter intensity starts tapering off. Otherwise, it should keep on increasing with the atomic weight of the specimen, atomic weight of the phase that you are having in the specimen, right. So, with more and more atomic weight, a greater proportion of the incident energy is getting absorbed by the sample, because of which you do not get a major increase in the yield of backscattered electrons beyond a certain point. Okay. And the yield is related to the weight by a polynomial function, and the atomic weight in that polynomial function you have a third order polynomial, you have a z cube sort of a behavior. So, this is not really a simple function to track. So, that polynomial function gives approximately the dependence of the backscattered electron yield on the weight. Yeah.
Will the secondary electrons coming from the,
If this is your sample, the backscatter detector is right on top, secondary electron detector is here, right. So, what is happening is the secondary electron yield is only from the surface, and because the electrons are low energy, they are getting captured by the positive potential, that is 100 to 300 volts that you apply in the Faraday cage, right. So, it is very rare that some secondary electrons will deflect all the way and go to the backscatter detector. It may happen because lot of electrons are getting generated on the surface. Some electrons may have sufficient energy to actually go right up, but the charge here with the Faraday cage will be able to pull many of these low energy electrons towards the cage, and you may not have any specific instances of these electrons going to the backscatter. So, for example, if you have a very flat specimen and you are trying to look at it with a secondary electron detector, okay, you will not really see much of an effect, because in a flat specimen you have almost an equal number of electrons from the surface that will go towards the secondary electron detector. So, there will be no difference in the surface morphology, right. You will not be able to appreciate that if the specimen is flat, okay. But if you are trying to observe the flat specimen, or rather a fractured specimen with the backscatter, then again you have a problem, because you do not really get a proper scattering, all your electrons are going towards the side because you do not have a level surface. So, for each of them you need to have sample preparation done in a different way. So, what information can be obtained from SEM? One is obviously topography, that means the surface features of the object and how it looks generally, the texture, and all these obviously have a direct relationship with the material properties, because for example, in metals, for instance, if you actually have a tension test performed on steel and you look at the fracture surface, the shape of the fracture surface is very much defined by the ductile behavior of the steel, right. Morphology is obviously the shape and size of particles making up the object. So, if you are looking at specific crystalline features in your material, for example, in cement hydration we know that we form calcium hydroxide and ettringite, and these are very well defined crystalline species, and you will see later that we can actually make out the size and shape of these crystalline objects that are forming as a result of cement hydration. The composition is because your backscatter density is a function of the atomic weight. So, when you are looking at a flat polished sample, right, the phases that appear bright obviously have a higher atomic number or atomic density as opposed to the phases that appear dark. If you are looking at a void or a pore, you will get almost zero reflectivity, or your surface will look black if it is a pore. You can also extract crystallographic information in terms of how the atoms are arranged in the object. However, to get to this level you may have to actually go to much finer resolutions. You will not be able to get this from a simple secondary electron image. You will have to go at very high magnifications to really make out crystallographic properties of different types of crystalline species that are forming in your object. So, that is something which is little difficult with typical SEM, but then you can actually get there if you have materials that are capable of getting resolved at that scale. Now, again similar to optical microscopy, we also have the same sort of terminology as far as SEM is concerned. Of course, magnification, you are just making a small location appear larger, okay. But what is magnification in terms of SEM? What you are simply doing is you are decreasing the scanning area, okay. So, please remember in SEM, if this is your sample, your scanning coil is scanning a certain area here, okay. If in the same area you take a smaller area and scan it, that is basically magnification, because your ultimate size of the screen is the same on which you are seeing the image, right. So, you scan a small area and transmit that to a large screen as opposed to scanning a large area and transmitting the same screen. So, magnification simply means that your scanned area is getting smaller. Okay. Resolution, same effect here, it is the ability to resolve two closely spaced points, right. Resolution is not the same as magnification. I keep repeating that because very often when people want to look at features more closely, they tend to increase magnification, but we learnt earlier that when you increase magnification, the confusion also increases. Because of the confusion increasing, the resolution becomes lower. So, magnification and resolution are not the same, although in electron microscopy you can get good resolution and high magnification. Okay. Now, one important factor which governs the resolution is obviously the size of the electron beam. Now, let us just go back to the secondary electron image that I showed you earlier, right. So, here if this electron beam was wide, if my electron beam was like that, if the diameter of the electron beam was even bigger than the relief features that I see on the object, I will not be able to make out these crests and troughs easily, right. To ensure that I pick up each and every individual point on the surface properly, I need now to have an electron beam that has a small enough diameter. Okay. So, that small enough diameter will ensure that I am able to resolve very closely spaced points. Okay. The depth of field obviously is the height over which a sample can be clearly focused, same thing as you see in photography or in optical microscopy. Spot size is the same size of the electron beam, the diameter of the beam of electrons. So, again smaller the diameter, the greater will be the resolution. So, how do you control the diameter of the electron beam? By the aperture which is provided in the objective lens. In the objective lens system, you have the aperture, you can control the size of the aperture that allows the electron beam width to be defined. Okay. So, working distance is the distance between the bottom of the SEM column and top of the sample. As I said, when you have short working distances, you can get better resolution, but lower depth of field. Again, coming back to this fact here, yeah, if you have a shorter working distance, right, you have a stronger current that is hitting the sample. If you have a longer working distance, your current becomes weak. So, as a result of stronger current, you ultimately get a better resolution. But please remember, always you have this compromise between resolution and depth of field. If you want greater resolution, you will be having less depth of field.